It's a pleasure to have Jonguk with us online from the University of Zurich. And Jonguk is going to talk on infinitely renormalizable critical points in 2D. Thanks, Jonguk.
Thanks, Marcel. And thanks to the organizers for the invitation to present this talk. And I do apologize for giving this talk online rather than in person. So I will be talking about dynamics in 2 dimensions, but I'll try to relate the discussion as much as I can to the 1-dimensional case. So even if you have no background in higher dimensional dynamics, hopefully this talk will be still accessible. So in that spirit, let's start with some general remarks about dynamics of rational maps in 1 dimension. So hopefully these won't sound too controversial. So the first thing I want to say is that if you wanted to control the geometry of the dynamics of rational maps, it's more or less equivalent to controlling the behavior of the critical points, because the critical points are where the distortion blows up. So those are the most dangerous spots in your phase space. But if the critical points are non-recurrent, then they're actually quite harmless. They're easy to deal with, right? So if you want something interesting to happen, then you want recurrence of the critical points. And the strongest kind of recurrence that you can have is this notion of infinite renormalizability, which I'll define more rigorously later. But for now, just think of it as being almost periodic or quasi-periodic. Well, actually, I guess this isn't really true. The strongest kind of recurrence is when you have exact periodicity. But of course, if you have a critical point which is exactly periodic, that's also easy to deal with as well. So this is the kind of the most difficult kind of critical recurrence that you can have. And the theory that needs to be developed in order to deal with such critical points are usually quite deep, quite involved, and quite delicate, as the previous 2 talks have hopefully demonstrated. And this kind of motivates the topic of my talk, because critical points, and particular infinitely renormalizable critical points, are very interesting objects to study in the context of dimension 2. So if you are trying to observe different critical behavior, the simplest setting in which you can do this is in the class of unimodal dynamical systems, unimodal maps on an interval. So here's the definition. So a unimodal map on an interval is a function which is at least C2, and it has a unique critical point of, let's say, a unique simple critical point. And I think it's instructive to visualize how it reshapes the interval when it acts. So let's say you have this interval I, and you have a unimodal map acting on this interval. So that means that it has a unique critical point, let's say C0. And this point is mapped to a critical value, which in this talk we'll denote by C1. So it's the first image of the critical point. And how this unimodal map maps the interval is it takes this interval and it folds it at the critical point, and then it places the critical point, the fold, at the where the critical value is, right? So it takes this interval and then it folds it like this, and then it lines up the fold to match up with the critical value, like so. And the way I drew it, I drew the 2 branches of the unimodal map to be separated, but of course it's actually 1-dimensional, so they should be completely collapsed. Yeah? So the action of the unimodal map is this folding of the interval like this. And the standard family of examples of unimodal maps is the real quadratic family. So the family defined by the formula x² plus a. And this is obviously unimodal. It has a unique critical point at 0. And you can also see it as an interval map if you restrict the parameter a to the range -2 to 1/4. This is precisely the intersection of the real line with the Mandelbrot set. So this is -2, this is 1/4. And when you restrict to this interval of parameters, then your quadratic polynomial fa will actually leave an interval invariant. Namely, you have, say, the beta fixed point and you have the critical point 0, and you have the pre-image of the beta fixed point. Well, then on this interval, the map will be a self-mapping. So it'll take this interval, and then it'll fold it at 0, and then it will place it like so. So the endpoints map to beta, and the critical point maps to the critical value, which is given by A. So this is the critical point, and this is the critical value, like this. Right? So A controls how much, after the fold, how much this folded image is stretched onto this invariant interval, right? So if you start with A equal to 0, which is approximately here, well, then you fold this interval, and then you leave the fold exactly where it was at 0. And then as you move A towards the left, you start to stretch this folded interval more and more towards the right. And when you get to the endpoint of this parameter range, then actually your fold will extend all the way over your invariant interval like this, right? So it'll be a full folding and then stretching all the way over the interval that you started with. Yeah? So as this parameter gets moves to the left, it's the behavior of the critical point becomes more and more complicated, right? So for example, I think people know that when you move from one satellite component of the Mandelbrot set to another, the map becomes more and more renormalizable. And then in the limit, you approach the first infinitely renormalizable quadratic polynomial, which is the Feigenbaum quadratic polynomial, right? Okay, so what does it mean for a unimodal map, or more generally an interval map, to be renormalizable? So first of all, so renormalization is quite a versatile concept. You can try to renormalize all kinds of different dynamical systems, and the precise definition of renormalization depends on the specific nature of the dynamical system you're considering. But in general, if you want to say that a dynamical system is renormalizable, typically what you mean is you have a dynamical system and it exhibits some kind of self-similarity, which is acting on a smaller scale and happens over a longer period of time. That's sort of a loose way of defining renormalization. So in particular, if you have an interval map, so let's say you have a map on an interval, I, this is F, then you would say that this interval map is renormalizable if it has a periodic subinterval J. So it has some interval J, and it's periodic in the sense that after some iterate P greater than 1, it maps back into the original interval it came up with. Right? So let's say this interval is mapped here, it maps here, and then it comes back. Some image like this, let's say, right? So then this, such a map would be renormalizable, because if you consider the renormalization of this function, which is, as it was in the previous two talks, the first return map to this subinterval, periodic subinterval. So in this case, the first return map would be F composed with itself P times. Then you get this interval mapping into itself. So you get another interval map. So you have the self-similarity, and it's acting on a smaller scale, the scale of J, which is smaller than your original scale. And it happens over a longer period of time, P, which is greater than 1, right? So that would be a renormalizable interval map. And if you have something which is infinitely renormalizable, that means that this periodic subinterval has itself a periodic subinterval, which again has a periodic subinterval, and so on, right? So if it's twice renormalizable, it has another periodic subinterval within. And if this happens infinitely many times, then we can take, then we have this infinite nest of periodic intervals. And if we take the intersection, then we end up with some limit set, which we will refer to as the renormalization limit set. So this limit set will be something which is Cantor-like, but a priori, you don't really know that it actually is a Cantor set. So in particular, you don't know that all the connected components are singletons, right? Because it could happen that there's some distortion in the geometry and some pieces might not actually shrink to individual points, right? So, but you have this renormalization limit set as long as your map is infinitely normalizable. And what you can show is that in the case of unimodal maps, this renormalization limit set is actually the closure of the post-critical set if F is unimodal. So if it's unimodal, then you have this unique critical orbit. And if it's infinitely normalizable, then the closure of this orbit will actually give you the intersection of this nest of periodic intervals. Okay. So here's an example. The classic example of an infinitely renormalizable quadratic polynomial, which we mentioned is the Feigenbaum quadratic polynomial. So here, let's label, so this is the phase space, and let's label some of the points. So first of all, we have the beta fixed point here, and its pre-image, which is -b. And we also have the alpha fixed point. So it's another fixed point with negative eigenvalue, and this will be the landing of the external rays 1/3 and 2/3, like so. And it has the critical point 0, which is right here, which will map to a critical value, which I think is approximately, it's probably around here somewhere, which is equal to this parameter value, which is approximately -1.4. So it's somewhere here. So this is A star. So this is the critical point. This is the critical value. And if you keep mapping it, I think this will map to somewhere here. So this goes somewhere here, like so. This is A, this is the second image of the critical point. I'll call that C2. And if you map it again, it maps inside and so on and so on. Yeah. So we want to, let's try to apply this definition of renormalization and show that this is at least once renormalizable. It's actually infinitely renormalizable, but we'll show that it's once renormalizable. So the way you do that is you have to find the subinterval, which is periodic, right? So for Feigenbaum, the periods will be 2 to the n for any n. So a subinterval that you can choose, I mean, there isn't a unique choice, but a reasonably simple choice would be to take the interval from, say, the critical value and the alpha fixed point, like this. So let's declare that to be J. Then if you iterate once, alpha has negative eigenvalues, so it flips the picture, right? So this interval will be flipped onto this interval right here. So this is F of J. And then if you iterate it one more time, this interval will fold onto where it originally came from. So it'll fold like this. Oh, actually, no, it doesn't fold all the way. It folds like this. Yeah. So you can see that after 2 iterates, the interval maps back into where it came from. And you can see the self-similarity because this return map, the second iterate, is again a unimodal map, right? Because it only was folded once during its cycle. Okay, so this is again renormalizable. Okay, so now, and by what I said before, you have an infinite nest of periodic subintervals of period 2 to the n. And if you take the intersection of all of them, you get some Cantor set on the real line, which is the closure of the post-critical set, which is the closure of the orbit of 0, right? And the geometry of this limit set is controlled by renormalization theory. In particular, its geometry relative to the real line is controlled by something called real a priori bounds, and its geometry relative to the complex plane is controlled by what is called complex a priori bounds, both of which are now, I think, considered classical results. Okay, so that's kind of a background of what I'm going to talk about in the one-dimensional case. Now let's transition into two-dimensional dynamics, and probably maybe the most gradual way we can do this is to first take the one-dimensional dynamical systems, which I understand very well, and try to identify it as a two-dimensional dynamical system, right? So let's say we have a one-dimensional dynamical system, then we can identify it as a two-dimensional map, iota of F. So it's an embedding of this one-dimensional map into 2 dimensions by doing the following. So the formula is here, you define it by this, but I think it's more useful to kind of try and picture how it shapes the space. So let's say you're in 2 dimensions, Right? So now you're transforming the plane rather than the line. So you have this map, iota f, the embedding of f, and how it shapes the space is as follows. So let's first draw the graph of f against the y-axis. So let's say the graph of f looks something like this. I don't know, I'm just going to draw an arbitrary graph here, there. Okay, so that's the graph of f against the y-axis. So this is this x-axis, y-axis, and this is the graph of f, like so. Then under this map, this space will be transformed as follows. So first, you take the space, the square, and then you collapse it onto something one-dimensional. So just a flat line like this. And then you're going to take this line and you wrap it around the graph of f, which is plotted against the y-axis, right? So you first collapse. So the first thing is you take the space and you collapse it onto an interval. And then you take this interval and then you take this interval and then you wrap it around the graph of f, like so. Okay, so this is the way it transforms. And if you want to know the dynamics of this map, then you would have to iterate this process, right? So you first collapse, you wrap, and then you apply again. So you collapse this curve, you flatten it, and then you wrap the image of that again onto the graph, and so on and so forth, right? So it might appear as though this action is something that's different than if you iterate this process, you might get something different than what you had in the one-dimensional case for just f. But if you just look at what you get, if you iterate this map, you see that you'll get equivalent dynamics under iteration of iota of f as you do with iteration of f. So let me just point out the dynamics of f identified as a two-dimensional system is really more or less equivalent with the dynamics of just f itself acting on an interval. Okay, so this is the way you identify a one-dimensional system as a two-dimensional system, and then you can try and see how the dynamic behavior changes if you extend, if you were to perturb this degenerate 2D map into an honest 2D map. So how would you make this into an actual 2D map rather than just a degenerate 2D map? Well, the only thing you would really need to change is instead of when you initially take your box and instead of collapsing it into a completely degenerate one-dimensional object, you leave it as a strip with some amount of thickness. And instead of wrapping a one-dimensional interval onto the graph, you take the strip and you put it as a little bend around the graph of f, right? Then you get an honest 2D map, which is non-degenerate. And probably the simplest example of a family of maps which does this is the Hénon map. So it does what I described previously for the quadratic family, right? So you have this quadratic family, and you have this map, which if you ignore this part, is just the embedding of the quadratic family into 2D. So what you will do is you would take, let's say, a quadratic polynomial fa, and you draw its graph over the y-axis. So this is the graph of fa. And this is the critical value a. And this is x-axis, and this is the y-axis. So the way this map transforms the space is it takes this box and it collapses it not onto just a one-dimensional line, if b is not equal to 0, but instead into a strip, and then it places that strip over this parabola, which corresponds to the graph of the underlying quadratic polynomial, which is f of a. So it would take this box and it would map it onto this strip like this. And the thickness of the strip will be b, or the absolute value of b, if b is not positive, like so. Okay. Yeah, so you can think that, so if b is equal to 0, then the dynamics of this Hénon map is just the dynamics of the one-dimensional quadratic polynomial. But you can see that as you make b bigger, is something positive, let's say, then you get something which is not just one-dimensional, but actually two-dimensional. And you can think of it as a small two-dimensional perturbation of the 1D dynamics, because what you will see, if you iterate for just, let's say, finite number of times, then the motion of the points is approximately corresponds with the motion in 1D, right? Because if you were to iterate this map where B is really small, then the position is more or less determined by the X coordinates, right? If B is really small, then the formula is more or less equal to this. So X coordinate kind of determines where you are. But if B is non-zero, then you get some contribution from the Y coordinate as well. So if you have a point and you map it by this Hénon map, it'll map to approximately where it should under the degenerate map, but then you get a small displacement from coming from the Y coordinates, right? So initially it looks kind of like exactly like the one-dimensional motion, but over time, this small errors from the contribution from the Y coordinate starts to accumulate, and then you get something truly two-dimensional rather than just one-dimensional. And you can consider the parameter family of all these Hénon maps. So you have this two-parameter family of Hénon maps like this, where so this is the family of Hénon maps, let's call it H. If you change the A value, that changes how much the graph, the underlying graph, one-dimensional graph, moves left or right. And if you change B, it changes the thickness of the strip that you map the square into, right? It changes how much you squeeze this box. And something I should point out is that this parameter value B is exactly equal to the Jacobian of your Hénon map. So you can think that if you have a two-dimensional, let's say, diffeomorphism, then its Jacobian is a measure of how far away it is from actually being just a degenerate one-dimensional system. Okay, so this is the Hénon map. And since when you let B equal to 0, so on this, when B is equal to 0, the Hénon family is actually just the quadratic family, or maybe more precisely, the embedding of the quadratic family when B is equal to 0. And for B is equal to 0, the dynamics of your maps are can be very well analyzed using renormalization theory. So we can hope that when you make B non-zero, you have some kind of renormalization theory that you can develop for such maps. So let's first try to define what it would mean for a two-dimensional map to be renormalizable. And the definition is actually quite natural. So let's say that you have a two-dimensional map, a diffeomorphism, which is at least C2, which takes, say, a Jordan disk into itself. Then we would say that it's renormalizable if it exhibits some kind of self-similarity. So it has another diffeomorphism mapping a subdisk into itself under a longer period of time, right? So it should have some sub-Jordan disk, let's call it D, which is periodic. Right? So under some first return map, which is F composed with itself P times, it takes the subdisk and it maps it strictly into itself, right? Then we would say that this thing is renormalizable. And again, if you are infinitely renormalizable, then we have an infinite nest of periodic subdisks, like so. And by taking the intersection, you get some kind of Cantor-like set in the limit, which we will call the renormalization limit set for this diffeomorphism, right? So the way I drew it, it kind of looks like it's an honest Cantor set where all the connected components are singletons, but again, a priori, you don't know that. Yeah? But something that you can show, something that I'll mention later, is that actually we can, for this two-dimensional diffeomorphism, you can also define a notion of unimodality, which I'll get to later. And if your diffeomorphism satisfies this two-dimensional unimodality condition, then you can also show that this renormalization limit set is actually just a Cantor set. and is actually the closure of the post-critical set of your map, if F is unimodal. So I'll put these in quotes because I haven't defined yet what it means for a diffeomorphism to have a critical point in 2 dimensions, and I haven't defined what it means for this diffeomorphism to be unimodal, right? So I'll do that later, but yeah, you have an analogous result as to the 1-dimension case. Something that I should point out right now, something that's important, is that if you have a renormalizable diffeomorphism, which is dissipative, so the Jacobian is less than 1, then renormalizations will degenerate into something like the embedding of a 1-dimensional map, right? And the reason is because, well, if you, the renormalization of your map, so the first return map is you compose your map multiple times, and the Jacobian on the composition just multiplies, right? So if the Jacobian is something less than 1, then if you take iterate of your map, then the Jacobian will just be exponentiated, and if it's less than 1, then it'll go to 0, right? So the first return maps for higher and higher renormalizations will degenerate to something like 1 dimension embedded into 2 dimension. So it's something important to keep in mind. Okay, so I define what it means for a 2-dimensional map to be renormalizable. For this definition to be justified, I should give you at least an example of a 2-dimensional map which is renormalizable, at least once renormalizable. And I should also tell you that actually there are maps which are infinitely renormalizable as well. So first, let me show you a map which is at least once renormalizable. And in fact, this is not too difficult. You can obtain such a map by taking a renormalizable 1D map, which is a technical condition that it doesn't have a parabolic orbit. Then if you take this map, embed it as a 2-dimensional map, and then you perturb it slightly within the Hénon family, what you'll get is still renormalized. So let me try to convince you that this is true by drawing some pictures. So first of all, so we went over how such a map transforms the space, right? It takes the square and it maps it to a strip around the graph of the underlying quadratic polynomial, right? But let's not start there yet. Let's first start with, okay, so let's say that this is the graph of the quadratic polynomial. Let me draw it like this. So this is the graph of your quadratic polynomial. But let's start initially with the 1-dimensional quadratic polynomial. So let's say your quadratic polynomial is once renormalizable. So it acts on the interval and it has some periodic orbits. Let me just take the same renormalization scheme as I showed in the Feigenbaum case, right? So in the Feigenbaum case, just pretend that FA is the Feigenbaum map. Then we showed that it was renormalizable by showing that, okay, it has this invariant interval from -b to b. It has an alpha fixed point somewhere here. And it has the critical point here, which maps to critical value here. And then which will map to some image C2, like so. Okay, and it has this periodic subinterval, which you can place right here. And so this is J. Then under one iterate, this will map to here. So this is F of J. And then under another iterate, it'll map back into this subinterval that you started from, right? So now let's show that if you were to embed this map into 2D as a degenerate 2D map, then it is still renormalizable in the sense that I defined here. It's not a diffeomorphism technically, but in the same sense, it takes some portion of your space and it maps it into itself under some period greater than 1. So what you would do is you take this strip right here, which lies over the alpha fixed point and the critical value. So you take this strip. And you can show that under the second iterate of this map, of this degenerate map, it'll map strictly back into itself, right? So the way you can convince yourself that that's true, so let me just plot some points here. So this is alpha, y coordinate alpha, this is C1, and I think this is C1, y coordinate, and then C2 is somewhere here, I think, C2. And this is C2. Okay, so how does this strip map? So when you first apply it, it'll just map onto just a flat piece, flat interval, and then it'll map onto the graph of this function over this piece. So it'll map onto, so this strip will map onto this interval right here. And then if you map it again, this interval will map back into this strip. In particular, it'll map to this portion of the graph right here, like so, right? So you took the strip and then you mapped it back into where it came from. So therefore it is renormalized in some degenerate sense, okay? And if you were to perturb this map, actually you just perturb this picture slightly, right? And by thickening the strip a little bit, you can still show that it maps strictly into itself. So if you were to perturb this picture a little bit, you can show that this strip, so if you were to take, let's say, HAB, which is some small perturbation of HA not 0, then you will map onto, so if you take a strip, which is approximately close to the strip that you had in the degenerate case, then it'll map onto a tiny strip like this under 2 iterates. So it's again renormalizable. Okay. All right. So then, so by perturbing slightly, you can preserve at least once renormalizability, and therefore you can preserve finite renormalizability. What about infinite renormalizable map? Is it possible to perturb it in such a way that it's still renormalizable, infinite renormalizable in this 2-dimensional sense? And the answer is yes. So this was done. So I think numerous authors have worked with this kind of in this kind of setting. I've mentioned in particular the works of these authors on the perturbation of the Feigenbaum quadratic polynomial. So they've proved a lot more than what is stated in this theorem, but for the sake of this talk, let me just state something basic that they've done, which is that in the Hénon family, if you look at the parameter space and you start with your Feigenbaum quadratic polynomial, which is infinitely renormalizable in the 1-dimensional sense. And if you were to perturb this map as a 2-dimensional map in the Hénon family, then what you can actually find is an analytic curve of Hénon maps, which I'm calling FB. So B is the y coordinates on this curve. And this FB will be infinitely renormalizable, and the renormalizations of any map on this curve will all converge to the same degenerate 1-dimensional limits. So if you start to renormalize infinitely many times, they'll all degenerate to the same 1-dimensional limit or embedding of a 1-dimensional limit. Yeah? But the caveat of this theorem is that it's a perturbative theorem. It uses the hyperbolicity of the renormalization operator and show that this hyperbolicity is preserved under some perturbation. So you can only get this curve for some very small epsilon. So the length of this curve, where your guaranteed infinite renormalizability is at present only epsilon long, and the conjecture, and this is what I'm trying to get right now, is that this curve actually extends to, so the conjecture is that this curve extends to Jacobian 1/4. Numerical evidence suggests that this curve actually extends all the way to Jacobian equal to 1. But I don't know, yeah, but here I think we have some tools to try and actually analyze what's going on here. I think it's kind of a mystery at present. Okay, so good. So for this talk, we want, so I'll give a result at the end about some progress that we've made towards this conjecture. But for now, let's focus on the dynamics of maps, which you can find on this curve, right? So we have, so there exists Hénon maps, which are infinitely renormalizable, which all converge to this 1-dimensional limit, right? So then what does the dynamics of such maps look like? And this picture shows that the dynamics looks pretty horrible, right? It doesn't look very nice. And this is, I think, a nice illustration of the fact that the question of geometric complexity, which is what this conference is about, seems to be fundamentally more difficult in higher dimensions than in one dimension. And the reason is that in one dimension, in order to understand the geometry, I think you only need to keep track of how distances are transformed under the dynamics. Whereas in two dimensions or higher, you also have to keep track of how directions are transformed under the dynamics. And this shows, so what this picture shows, the top picture is just the degenerate embedding of the Feigenbaum quadratic polynomial. So you have the graph, this one-dimensional graph, and this whole box is mapped to this one-dimensional graph, right? And as we said before, this is just an embedding of the quadratic polynomial, and the dynamics is the same. So for the one-dimensional quadratic polynomial, you have this renormalization limit set, which is a Cantor set on an interval. So for this map, you'll have the same Cantor set, except it's now plotted on the graph of the Feigenbaum polynomial. But since on the interval, this Cantor set has geometry well controlled by a priori bounds on the graph of the function, it also has nice geometry. And here we have a numerically computed candidate for an infinitely renormalizable Hénon map of Jacobian 0.2. So actually, we don't know that such a map exists, but we'll pretend that this thing actually is infinitely normalizable. So then under this map, you have something which doesn't map exactly onto the graph of the underlying quadratic polynomial, but it'll actually map onto a little strip around this graph, right? So if this thing is infinitely normalizable, then it'll also have a Cantor set, Cantor limit set, renormalization limit set, but now it won't be restricted to this curve. It'll be plotted in some neighborhood of this curve like this, right? And you can see that the geometry of this thing, to analyze the geometry of this thing, you have to deal with this transformation of directions. So what these, yep.
So what does this line represent?
What do these, yeah, so that's very good. So what these lines represent is they're secant lines through points in the Cantor set, through points in the renormalization limit set. So they're kind of direction lines that are tangent to the odometer. And you can see that in the one-dimensional case, of course, if you take a line which is tangent to the graph of the function, when you transform it, it'll still stay tangent to the graph of this function. Right? So we have a kind of a trivial transformation of lines. Well, maybe it'll look even more trivial if you look at how the one-dimensional quadratic polynomial maps. So the one-dimensional quadratic polynomial, it maps the interval to itself. And of course, if you take any line which is parallel to this interval, it'll just stay parallel to the interval that it acts on, right? So now with the 2D embedding, it just takes this interval and it just maps it to the graph, to the parabola, the graph of the quadratic polynomial. So you still have this invariant line, but it just now maps along this parabola like this. Right? So we don't have to worry about how the directions are twisting under the dynamics. The directions are just staying tangent to the parabola. But as soon as you change the Jacobian to something positive, and so you have some width where this Cantor set can lie. And now you can see that if you take a secant direction through 2 points in the Cantor set, they'll spin around as you map by the dynamics, right? So that means that the Cantor set, the way it's placed in the space, it'll have some kind of twisting to reflect this change in direction. So in order to understand the geometric complexity of this dynamics, you'll have to keep track of how the directions are moving. And okay, I have 10 minutes. How much time do I have?
Yes, 10
okay,
minutes.
10 minutes, okay, good, all right. So in the next 3 slides, I'll try to give an idea of how this can be done. So we'll start with the standard way of keeping track of directions in higher dimensional dynamics, which is what I'm calling the measurable Pessin theory, right? So let's stick with the infinitely renormalizable diffeomorphism. So let's say you have F acting on some Jordan domain and it's infinitely renormalizable. So it has this nest of periodic subintervals, subdomains like this. And then you can take a nested intersection to get some limit sets. So this is the Cantor set that you get. And just using standard Poisson theory, you can show that on this Cantor set, it's uniquely ergodic, and respect to this unique ergodic measure, the Lyapunov exponents are 0 and something negative. So what does this mean? So first of all, what does it mean, Lyapunov exponents? And what does it mean for one of them to be 0 and one of them to be something negative? So what this means is that for a typical point, in the sense of full measure with respect to the unique ergodic measure. So if you take a typical point, so let me take one point, and so P is in the Cantor limit set, then there exists a direction, which we're calling the stable direction at P. And there exists another direction, which we're calling the center direction at P. And if you look at the growth rate, the average growth rates along this direction of the derivative of the iterates of f, then it will average out along the stable direction. It'll, on average, grow like lambda to the n, or rather shrink, contract like lambda to the n as you go forward in time. So as you go forward in time, along this dynamically defined stable direction at P, the derivative of your map will contract this direction almost exponentially with some error, some deviations, but on average over a long period of time, it'll contract like lambda to the n, where lambda is something less than 1, right? And that means if you go backwards, it will actually expand like 1 over n, right? So if you start going backwards, it'll expand like 1 over n along the stable direction. So that's what it means for one of the Lyapunov exponents to be log lambda. So Lyapunov exponent is like log of the average growth rate that you experience. And the fact that you have Lyapunov exponent 0 means that along the center direction, if you start going forward or backward in time, the average growth rate will be something close to neutral. So the average growth rate will be something close to 1 as you go forward or backward in time. So there's no exponential expansion or contraction as you go in either direction along the center direction. So this is what measurable Poisson theory will tell you. Standard measurable Poisson theory will tell you. It will tell you the behavior and the dynamically defined directions for a full measure set of points. But the measurable Poisson theory isn't really enough to describe what's going on here, because, well, it omits, it allows it to omit sets of measure 0, but of course we're trying to see the effect of having a critical orbit for a infinitely renormalizable map, 2D map, and a critical orbit is countable, so it has measure 0, right? So measurable Poisson theory will not be able to see the effect of a single orbit, such as the critical orbit. So what we need to use instead is something a little more hands-on, a little more direct, which I'm calling quantitative Poisson theory. So idea with this quantitative Poisson theory is you try to get a similar kind of analysis of how the dynamics act on directions at points, but you allow yourself to consider all points in your invariant set, but you have to give explicit estimates, and you have to assign explicit directions to the points that you want to consider. Okay, so quantitative Poisson theory is like hands-on version of measurable Poisson theory, but you allow yourself to analyze any points rather than just a full set of, rather than just a typical point. So this, what's written on this slide will be probably very difficult to kind of understand if you just take a look at it. Let me try to explain with a picture. Okay, so another important aspect of quantitative Poisson theory is that in measurable Poisson theory, you enforce, because you're allowed to throw away sets of measure 0. You enforce that the points that you're looking at, the points that you're describing, behave well as you go forward and backward in time. Whereas in quantitative Poisson theory, we break this the fact that you have to deal with 2 directions of time at once, right? So we can consider forward in time and backward in time separately. So we define what it means for a point to be regular. So regular in this kind of nice sense of having a well-defined dynamical direction, if it satisfies this condition. So what this means is, let's say you have a point, P0, and you have the orbit of this point. P2, and you have the backward orbit of this point as well. So we would say that this point is forward regular if you can find a direction, which I'm calling the stable direction at this point, so that if you transform along this direction by the dynamics, then you experience something close to exponential contraction by lambda, right? But there might be some deviations, especially near the beginning. So you allow some error term. So you allow, it might initially be not contracting exponentially. So you multiply by some constant bigger than 1. And you also allow some kind of deviations in the exponent, right? So you allow delta deviation in the exponent. So this is something approximately like an exponential contraction along this direction. Then we would say that this point is forward regular. And if you have a direction, which we're calling the center direction at point P naught, along which as you go backward, you experience almost neutral growth. So not too big of a growth. So if delta is really small, then if you exponentiate by delta, then you get something which is close to 1, right? So if along this direction, the derivative, the growth rate of the derivative along this direction is something almost neutral with some error, L and delta, then we would say that it's backward regular like this. And we would say if you can combine both of them and ensure that you have some angle here.
So, sorry, what is lambda?
Oh,
some
lambda,
specific fixed number?
Lambda is the Lyapunov exponent.
Ah, okay.
So the
right.
typical
Sorry,
contraction rate.
All right, thank you.
Point.
Okay.
Yep. And if you can guarantee that the angle between the stable and the center direction is at least 1 over L, then we would say that it is actually Poisson L regular. This orbit is Poisson L regular. So what does this give you? What do these 3 conditions give you? I have 2 minutes. So what this gives you is that you can pick out an exponentially shrinking neighborhood around the orbit of P naught. So the initial radius of this neighborhood will be 1 over L, where L is this error bound that you give on the contraction rate along these directions. And then as you chase the orbit of this point forward and backward, you keep the same initial radius, but you shrink it exponentially by lambda to the delta. So the radius of this will be 1 over L lambda to the delta, 1 over L lambda to delta, and so on. And same thing as you go backward, 1 over lambda delta, 1 over lambda to delta. So you have a disk, let's say dn, which is equal to 1 over L lambda to the delta n radius centered at Cn, or no, Pn. Okay, so you can draw these neighborhoods, which are called the regular neighborhoods of this regular orbit. And what you can do, given these conditions, so given, let's say, number 1, what you can do with the forward orbit of P naught is you can do a change of coordinates on these regular neighborhoods, so that if you remain inside the regular neighborhood under the dynamics, then it actually just looks exactly like mapping by a linear map. In fact, a diagonal linear map. So you map by the dynamics. And as long as you stay within a small enough neighborhood so that under your iterates, you stay inside the regular neighborhoods as you go forward, your dynamics will resemble just the dynamics of a diagonal map, which in the horizontal direction is just neutral, and in the vertical direction is contracting by exactly lambda, like this. Right? And then in this case, you can actually take the vertical axis in this linearized neighborhood and then pull it back. And what you get is a curve, a smooth curve, which will actually be the stable manifold at P naught, like this. Right? And so this is the curve which under the dynamics will shrink exponentially to P naught. And you can, if you have condition 2 instead, then you can do the same thing with the backward orbit. So you can linearize these neighborhoods and as long as you stay inside the neighborhood, your map looks exactly like just a linear map. Like this. And what condition 3 gives you is that, so if you have some angle between the stable and the center direction, you can actually glue these two linearizations together so that you actually get this full chain of linearization of your dynamics. So this is, I think, the best tool that we have to analyze how directions are transforming under dynamics in higher dimensions. Okay, and if, let's say, this constant L, this controls how regular your point is, so how much of a neighborhood, how big of a neighborhood you can linearize your dynamics. So this L is called the regularity constant. And if you stay within the set of some uniformly bounded regularity constant, then your dynamics kind of behaves exactly like a one-dimensional dynamical system, right? Because you have this factorization of your space into stable direction and the center direction. And along the stable direction, all that's happening is just exponential contraction. And the dynamically relevant direction is the center direction, right? Okay, and now I'm over time. Let me just define a critical point, and then so let me just take 2 more minutes, sorry. So what is a critical point? So a critical point is the break in this third condition. So if you have a point, let's say C naught, and you are forward regular. So as you, so you have a critical point. So you have a point whose orbit you chase like this, -1, C -2. And let's say you have some direction, which we're calling the critical direction, along which you have the following property, that if you go forward in time, you satisfy this condition. So as you go forward in time, starting from the critical point, you experience exponential contraction by lambda. And if you go backward in time, you experience 2 along this direction. So as you go backward, you don't experience expansion, but you experience neutral growth along the same direction, right? And moreover, so we've discussed how if you have this forward regularity behavior, then you can have this stable manifold at your point. And if you have backward regularity behavior, I didn't mention this before, but what you can do is you can take the horizontal axis and then pull that up to the regular neighborhood, and that will give you what is called a center manifold at your point. So since for this critical point, you have backward regularity, you also get the center manifold at this orbit point, right? So we would say that this point is a quadratic critical point, regular quadratic critical point, if it has this forward regularity and it has this backward regularity, and the invariant manifolds that you construct using this regularity has a quadratic tangency at the critical point. Then we would say that this is a quadratic critical point. And what happens with this is that if you were to uniformize such an orbit, then you don't get this linearization where it's just linear all the way. If you have this kind of picture instead, then when you uniformize this orbit, what you actually have is, if you start going forward from the critical value, your map looks like a linear map. And if you go up to the critical point, your map looks like a linear map. But then in the transition from the critical point to the critical value, you actually have to map the horizontal axis onto a sideways parabola against the vertical axis, right? Which is exactly what the Hénon map does. So in between transition from the critical point to the critical value, your map will actually look something like, let's say, this. So this is quadratic critical point for a higher dimensional map. And we would say that your map is unimodal if outside of the regular neighborhood, the uniformization neighborhoods of this critical orbit, you just have some uniform bound on the Bayesian regularity. And what you can show, let me just end it here, that for these maps that we discussed, this infinitely renormalizable maps, which contract to a one-dimensional limit, all of these maps with this horrible picture are unimodal. So this twist in the direction can be explained by this one critical orbit. Okay, I'm over time, so let me stop here. Thank you.
Thank you very much, Jonguk, for the very interesting talk. Is there any quick question, because we're running behind of schedule? In the room or online?
Could you show your last slide?
Oh, yeah. There.
The theorem. Thank you.
Mm-hmm. Yeah. So it basically says that if your Jacobian is less than 1/4, then you know that there's some epsilon height where you have infinite renormalizability and also contraction to the right limit. So all these maps will be unimodal. And if you can find an infinite renormalizable map up here, which is unimodal, then it actually has to also converge to the same limit, right? So all that's left, and this is what we're trying to do now, is that up to height 1/4, if you're infinitely renormalizable, then you're unimodal. That would allow us to prove that this thing actually extends all the way to 1/4.
Jonguk, just to make sure, so this is the conjecture about the behavior of this adding machine in the Hénon map, but it doesn't tell anything about other kind of phenomena. So there might be some other interesting phenomena that happen outside of the renormalization.
Yes. So it actually, there will be interesting phenomenon. For example, so I think Dixing, who is here, have convinced me that let's say the conjecture is true and the infinitely renormalizable parameters do extend all the way to 1/4 like this. Well, then you can actually track the, let's say, the hyperbolic basin coming from the airplane. Let's say these are the airplane quadratic polynomials. If you track that sink in the Hénon family, it will actually overlap like this. So you will have maps which on one part of its phase space is infinitely period doubling renormalizable, but on another part it has a tripling sink, period 3 sink. And how?
And just quick yes and no question. Do you understand what would happen in the dynamical plane? Yes, no, 50%.
Okay, so if I had to choose between yes and no, no. But there's some hope of figuring out what's happening. Yeah.
Okay, this is like when the airplane crashes into the basilica, right?
That's right, exactly. Yes.
Kind of.
Yeah.
And then before it crashes into the basilica, there is this it passes through the Feigenbaum curve. Okay.
Yeah, exactly. Mm-hmm.
Okay, I suggest we keep any further questions or comments to be communicated via email, because we are really running behind the schedule and there is a very tight launch schedule. So let's thank Jonguk for the really beautiful talk again.